Given a signed 32-bit integer, we need to reverse the digits and return the result. But if reversing it causes the value to go outside of the signed 32-bit integer range, then we just return 0 instead. And lastly, we have to assume that the environment does not allow us to store 64-bit integers, only 32-bit. So first, I'll do a quick review of how bits work in case anyone needs a refresher. So a bit is short for binary digits and can only either be a 0 or a 1. If you wanted to use bits to represent integers, then with only one bit, you'd be able to encode two integers, which would be 0 and 1. If you had 2 bits, then you would have 2 options for the first digit and 2 options for the second digit, which means you could encode 4 integers, which would be 0 to 3. If you had 4 bits, then by the same logic, you could encode 2 to the 4th power integers, which would be 0 to 15. So here, we're working with 32-bit integers, which means that you could encode a total of 2 to the 32nd power integers, which would be 0 to 2 to the 32nd power minus 1. However, this only applies to unsigned integers, which means only 0 and positive numbers. If we wanted to include negative numbers, we'd have to use signed integers. With signed integers, the leftmost bit indicates the sign of the number, so it'll be 1 if the number is negative, and 0 if it's positive. This means that we only have 31 bits left to work with, so the maximum integer is 2 to the 31st power minus 1, and the minimum turns out to be negative 2 to the 31st power. Now, in languages such as Java or C, the int data type corresponds to a 32-bit integer. If you needed a wider range of values, you would have to use the long data type, which is a 64-bit integer. So this problem is basically asking you to assume that you can only use the int data type. Now, we're going to be using Python to solve this, which works a little differently because Python will actually adjust the size of the integer for you. But we can still solve this problem by just assuming that we're unable to store anything larger than 32 bits. Now let's look at the code and solve this. Let's say that the given integer x is 123, so we'll need to reverse the digits and return 321 as our final result. The first thing we'll do is establish the maximum and minimum range of 32-bit integers, which we discussed earlier, and I've also written down the full numbers for reference. Then we'll create a variable called reverse and initialize it to 0, and this is what's going to hold the reversed integer. We'll then enter a loop that will transfer each digit in reversed order from x to reverse, and this will keep going until x equals 0. Now, since we're assuming that the environment cannot hold anything larger than 32-bit integers, we need to check if there's going to be overflow before adding a digit to reverse, not after. So here, if reverse is greater than maxint divided by 10, then that means that when we add on the next digit to reverse, it'll be greater than maxint. And it's similar logic for minint as well. If reverse is less than minint divided by 10, then after adding the next digit, reverse will be less than minint. So in those cases, we would just return 0. You'll see an example of how this works later, but for now, I want to focus on the reversing part of the algorithm. So first, we'll extract the digit in the ones place of x by using the modulo operator. Remember, modulo will return the remainder after division. So here, x mod 10 is the remainder of 123 divided by 10, which is 3. Now, the reason why I have this if-else statement here is because the modulo in Python works a little differently from other languages, and we actually need to use negative 10 instead of 10 if x is negative. I'll go into more detail in the next example when we use a negative number, but for now, let's finish up this example. So then, we're going to transfer that digit over to reverse, and the way we'll do that is by first multiplying reverse by 10 to make room for the new digit, and then adding on that digit. So in this case, 0 times 10 is still 0, and then we'll add 3, so now reverse is 3. The last step is to remove the digit we just transferred, 3, from x, and we'll do that by first dividing x by 10 and then using the trunc function from the standard math library. So truncating a number will simply get rid of everything past the decimal point. So 123 divided by 10 equals 12.3, then truncated will just be 12. Now you may be asking, isn't this the same thing as using floor division and rounding down? Well, for positive numbers, yes. But the reason why we truncate instead is because of negative numbers. For a negative number, we actually want to round up towards 0, not down away from 0. Again, I'll show you an example of this using a negative number next, so let's carry on for now. We loop again and make sure that there will be no overflow. We then extract the ones digit by doing 12 mod 10, which is 2. Then we'll add it to reverse. 3 times 10 is 30, and 30 plus 2 is 32. Then we'll get rid of the 2 from x by doing 12 divided by 10, which is 1.2, then truncated is just 1. At this point, we've successfully reversed 2 digits and brought them over to reverse, and we only have one more digit to go. So 1 mod 10 is 1, and 32 times 10 is 320, plus 1 equals 321. Finally, 1 divided by 10 is 0.1, and then truncated is just 0. Now x does equal 0, so we exit the loop and return reverse. And as you can see, we reversed 123 so that it's now 321, and we're done. Now let's do an example with a negative number. Let's say it's negative 456, so when we're done, we should return negative 654. Again, let's establish the max and min integers and set reverse equal to 0. X does not equal 0, and reverse is not less than min int, so let's go ahead and extract the ones digit. X is negative here, so we'll have to do negative 456 mod negative 10. Now, the reason why you need to use negative 10 instead of 10 is that in Python, a modulo operation will always return a number that is the same sign as the divisor, which in this case is the 10 or negative 10. So if we want the digit to be negative 6, then we would have to do x mod negative 10. And in fact, if you try to do negative 456 mod 10, you would actually end up getting 4 as your result. Now, I know that seems weird, and if you want to know why Python does this, I'd encourage you to look it up and read all about it. But for this video, I'm just going to say that when using the modulo operator with negative numbers, if you want it to behave the same way as it does with positive numbers, but just have the result be negative, you need to make sure that the divisor is also negative. And again, other languages like Java or C don't behave this way, so this is kind of a Python-specific thing. So moving on, 0 plus negative 6 is negative 6. And lastly, negative 456 divided by 10 is negative 45.6, and then truncated is just negative 45. Now, if we used floor division here, then negative 45.6 would have been rounded down to negative 46, which is not what we want. So that's why it's important to truncate the number instead of using floor division. So next, negative 45 mod negative 10 is negative 5. Then, negative 6 times 10 is negative 60, and negative 60 plus negative 5 is negative 65. Then, negative 45 divided by 10 is negative 4.5, and then truncated is negative 4. And it's the same thing for the last iteration. The digit is negative 4, reverse becomes negative 654, and x becomes 0. Then we're done, and we return negative 654. Now for the last example, I wanted to do one where reversing the integer results in overflow. Let's use this really long integer here, which when reversed turns out to be 2,147,483,651. So it's just above the maximum integer. So by now, I'm sure you're familiar with how the reversing algorithm works. So I'm just going to let this run so we can get to the end. The loop will keep running and reverse each digit, and reverse doesn't go over the maximum integer until near the end. Okay, so now that we're almost done, let's slow it down. We've gotten to the point where x is 15, so there's 2 more digits to reverse. The digit to extract is 5, and then we'll add that on to reverse. Then x is updated to be 1. Now on the final iteration, when we check this condition, max int divided by 10 is 214,748,364.7. But reverse is 214,748,365. So this condition is true. So that means that if we added one more digit to reverse, it would result in overflow and be greater than max int. So we'll stop here and just return 0, which means that reversing x is not possible because it results in overflow. Now, before I end this, I want to address one last thing that some of you may be asking. You may be saying, when we check this condition, don't we also need to check the value of the last digit? In other words, what if the reverse digit is less than max int divided by 10, so we think it's fine, but when we add on the last digit is, let's say, 8. So now the new integer is greater than max int, and the overflow goes undetected. Is this possible? Well, thankfully, we don't need to worry about this, because if the last ones digit was an 8 or a 9, then that means the original integer, which was reversed, was already out of the 32-bit range. So it would have been impossible to receive this number as an input, since the environment doesn't allow us to store 32-bit integers. The LeetCode question also explicitly tells us that the input will be within the signed 32-bit integer range, which is why we don't need to check to see what the last digit is. And so the reason this works is because the rightmost digit of the maximum integer is greater than the leftmost digit. Because of this, I know that even if the original integer has the same number of digits as maxint, the leftmost digit must have been 2 or less. Therefore, when the original integer is reversed, I know that the last digit to be added will never be greater than 7, so I know that this will never cause overflow. So because of this property, we don't need to check the value of the digit that we add on to the reversed integer. But I wanted to mention this because if you were to do a similar type of problem where your maximum or minimum value didn't have this property, then you would have to check the value of the digit in order to avoid going over the maximum or minimum value.